Hello, and welcome to today's webcast, The Value of Single Source Providers of Emerging Contaminants Removal, including per and polyfluoroalkyl substances, brought to you by Water World Magazine and sponsored by Evoqua. My name is Alana Maya. I'm Chief Editor for Water World, and I'll be your moderator today. A few housekeeping items before we begin. Today's audio, video, and slides for today's presentation will be pushed to your screen automatically, and a PDF of those slides is available in the event resources area, as well as some other resources from Evoqua, including 2 case studies that you may find helpful. If you're running pop-up blocking software, we recommend that you disable it to view this webcast. We also recommend that you close down any other applications for better performance. For any technical difficulties, please submit your issue through the Ask a Question box, and a member of our webcast support team will work with you to correct the problem. The Ask a Question box is also how you can submit questions for our presenters. We'll discuss your questions during the Q&A portion at the end of the program. A certificate of attendance will be issued automatically via email within 24 hours, and for your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive, and it will be accessible for 6 months at waterworld.com. One final request before we begin: your feedback is very important to us, and we hope that you'll take a moment to complete a brief satisfaction survey at the end of the broadcast. And now on with our program. We have 2 terrific presenters for you today. John Lombardo is Senior Product Manager with Evoqua Water Technologies as the Product Manager for the ProAct Environmental Services, or PES, division of Evoqua Water Technologies. His responsibilities include sales and marketing support, lifecycle management, and product innovation for activated carbon and media products and services. He also supports PFAS opportunities for municipal drinking water and short-term or temporary industrial and military clients, and he holds a Bachelor of Science in Chemical Engineering and a Master of Business Administration, and has been with Evoqua for more than 26 years. Jeff Pachelia is Senior Business Development Manager with Evoqua Water Technologies for emergency contaminants. Prior to joining Evoqua, he has held several senior leadership positions with SGS, Pace Analytical, and Vista. Jeff has specific expertise in emerging contaminants, developing analytical programs, and customer support to meet the needs of this ever-changing market. He has a BS in Business Administration with a concentration in Sales and Logistics from the University of Maine, Orono, and a minor in Chemistry from Duquesne University in Pittsburgh. And now, without further ado, I will turn the program over to Jeff.
Thanks, Alana. Hi, everybody. So, in a perfect world, there would be no emerging contaminants. Unfortunately, that's not the case. So we're going to talk about that today. Here's an outline of what we plan to cover today. I will cover the beginning overview and end with the wrap-up, and John will cover solutions and present some case studies. We'll save time at the end of the webinar to take questions. Now on to an intro about Evoqua. Evoqua Water Technologies is a leader provider of water and wastewater treatment solutions, offering a broad portfolio of products, services, and expertise to support industrial, municipal, and recreational customers. We offer emergency, mobile, and permanent water treatment solutions, and within these sectors listed above, employs one of the largest and most diverse mobile fleets in the country. We know water plays an instrumental role in so many aspects of daily life beyond drinking water. Evoqua provides solutions for customers with critical water needs across these key market segments like energy generation, wastewater, oil and gas, manufacturing, and many more. Today we have 160 locations and over 200,000 installations worldwide. So let's get into it. What's the current status of environmental compliance regulation? Well, it's an interesting question. So for water, currently EPA is being pressured to finalize regulation and evaluate further lifetime health advisories through their PFAS action plan. Just recently came out in the news, there's emerging EPA standards governing the discharge of wastewater containing PFAS. But nothing final yet. In the absence of EPA regulations, local states have taken the lead on setting their own state-by-state action levels, and in some cases are more stringent than current federal interim guidelines. For air and waste, there are potential indicators for regulations for PFAS as a hazardous substance. But again, that's not final. The current interim guidelines came out in 2020 using the Drinking Water EPA Lifetime Health Advisory for both PFOA and PFOS set at 70 part per trillion. And finally, there is limited data of known and detectable precursors within influent wastewater. With that, the need for improved analytical test methods that can also detect these compounds are coming. We do expect some of these later this year, potentially early 2022, maybe Q1, Q2, by the EPA. So contaminants enter the environment through various sources and eventually make their way into soils, groundwater, drinking water, and eventually us humans. This picture to the right tells the story. It all starts with a source. And some examples might be chemical manufacturers or producers, some commercial applications, a landfill, leachates, wastewater effluent, and even firefighting foam applications. All of these can contribute through exposure routes like occupational exposure, drinking water, atmospheric transport to contaminated food products, which over time can contribute to adverse health effects. One of the largest studies conducted for PFAS was the C8 health study in 2005-2006. The study looked at human blood serum and was performed on a population of almost 70,000 people who were affected by contaminated drinking water with the chemical name PFOA, as we know it, or C8. The study focused on 6 water districts across 2 states. And in the end, results showed elevated levels of PFOA in the population, and we have since learned these levels in our blood can cause several medical conditions. According to the CDC, lab results have linked adverse health effects to growth, development, reproduction, and liver infection. So John will talk about water treatment solutions and present some case studies.
Hello, can people hear me? I'm sorry, I think there was an audio issue. Jeff, can you hear me?
We can hear you, John.
Sorry about that. I don't know what happened. So anyway, my name's John Lombardo. I'll be taking it from here. My apologies. So talk about PFAS removal solutions. So there are 3 different solutions that are used for either capture or separation. The first is granular activated carbon. It's been named the best available technology by EPA for organic contaminant removal. It removes other organic contaminants as well as PFAS. So there's competitive absorption. It's pretty widely used for other things as well, chlorine removal, organics, other things. It comes with minimal maintenance, and it's pretty simple to use and pretty widely accepted even prior to use as an emerging contaminant removal for PFAS. A more recent development has been single pass ion exchange. The ion exchange process has been around for a long time, like sodium softening, things like that. It runs at a lower empty bed contact time, so it can go at a higher flow rate. So systems typically have a smaller footprint. There's no chemicals or liquid waste to deal with, and the spent resin can be incinerated. And it also comes with minimal maintenance as a flow through in a pressure vessel configuration, similar to GAC. Membranes, particularly RO and NF membranes, are very highly effective at removing or basically separating PFAS from a water stream. It does also remove other dissolved solids. However, you do end up with a smaller but more concentrated stream of contaminants at the end to deal with. There are certain applications, a few that we know of, that membranes have been chosen over either carbon or resin solely for the fact of the number of contaminants in the water, whether it's not just PFAS, but other things that may be in the water that have to be removed, kind of a veritable witch's brew of contaminants. So if you're not selectively removing, membranes are highly effective. So why does granular activated carbon work? So granular activated carbon is a highly porous media. It has an extremely large surface area, so there's a lot of room for contaminant adsorption. And that's an AD, not to be confused with an AB, absorption, very different processes. So the structure of the carbon has a lot to do with it. So that's why all carbons are not created equal. There are three main pore structures inside a granular activated carbon. There's the macropores, as highlighted there, which are the biggest pores, the largest pores. Then there are the mesopores, which are the medium pores or the middle pores. And then there are the micropores, which are the smallest. Adsorption actually takes place at the micropore. So as a contaminant is adsorbed, it moves its way down that pore to try and get into the most small area of the pore, the micropore. So really the mesopores, we call them transport pores. We kind of think of this as parking lots and highways. So the mesopores are the highways and the micropores are the parking spots. So the old adage, if you've ever been to a sporting or concert event, the roads getting in there and the parking spots. So if you have a lot of roads but small parking spots, you're going to end up sitting on the highway. And if you have a lot of parking spots but no roads getting in, you're going to end up being stuck in traffic at the end of the game. So both of those things you have to balance so you don't get impaired diffusion into the pore. So performance, how do you determine what carbon is best? Well, it all depends on what's coming in. We look at a combination of porosity and surface chemistry to determine which one's the best, and Evoqua does help do that to match the best performing carbon for the specific application. So a little bit about ion exchange. So why and how does ion exchange resin work? Ion exchange is based on a very simple principle of exchanging a harmless ion for the contaminant. So in the picture there above with the kind of the green specks as the contaminants and the yellow circles as in this case chloride, where we're using an anion exchange resin for removal of PFAS. So in this case, the contaminant exchanges a chloride and the contaminant stays on the resin, and actually the resin actually also has an adsorption feature to it. So it actually moves and migrates those contaminants down into the porosity of the structure. And then it exchanges basically the harmless chloride ion at the end. Because of this combination of exchange and adsorption, it basically uses a smaller footprint. So if space is an issue, ion exchange resin may be a better option, all depending upon what's in your water and other competing contaminants and other things along those lines. Life cycle costs are a little bit easier to predict because of the effects of ion exchange resin, and the spent resin can currently be incinerated. One of the things that we advocate and we find most other of our peers and all recommend is performance testing, right, to verify how you're going to, what you're going to see. And this also helps with CapEx and OpEx, right? So it's a really good thing to do up front. So there's really two types of testing. There's a pilot, which is the picture on the right, or a bench scale, which is basically done in a laboratory. And that can be used to test the effectiveness of the technology for removal. So it can help you predict things like throughput, breakthrough curves, things like that, how long you're going to get, so throughput values, and performance, right? How are you going to get for removal? What components may break through first, et cetera. So between a combination of pilots or bench scale, usually depending upon the timing and everything else, one takes a lot longer. Piloting is actually done on a slipstream of your feed water, and typically that can run, for anywhere from months to a year. Where bench scale testing can be a simulation of a full scale system that can be done in a couple of weeks' time. Accelerated bench scale can simulate months of runtime actually within days. One of the other things that's not on that, but there's also the availability of mobile units, right? When operation can't be interrupted, excuse me, or if there's an emergency situation, something rapid needs to happen. So Evoqua, and I know others, but Evoqua has emergency or rapid response equipment, trailers, vessels, other things, and we do it in more than drinking water applications. We can do it in construction site treatment or construction dewatering. We can do industrial process water treatment and industrial wastewater treatment. So basically, the configuration can be determined by your flow rate and your contaminants, and we have variable skid-mounted and tailored equipment to fit your site constraints. And this is actually a picture of a site in Michigan for a construction dewatering project. So mobile units are an effective and temporary way to get people out of a jam or to keep processes running when an emergency or an event occurs. So I'm going to talk a little bit now about some case studies. So we're going to talk about water treatment at a construction site and contaminant removal. This is a site up in Western Michigan that needed to be done in a quick timeline. It was installed about 6 months ago and is currently still active. They were doing some lakefront development, and there was a very high water table, and they found contaminants in the water, PFAS specifically, that needed to be treated for that dewatering to be discharged. So the city set treatment goals to non-detect. So, 0 is an infinite number to get to. So non-detect means that it's down to the current detection limits, which is a very important thing. 0 really is a very finite number. It's an infinite treatment, but a very finite number. For changing regulations and changing technologies, non-detect really is the way to go, just because it takes into account current standards. In this case, the treatment goal was met throughout the project and still operating, and it's been a good system for the end user, and it's been very easily maintained and serviced for the clients as well, for the construction company. We have another water treatment construction site. This one is in Muskegon. It was a temporary system, same type of thing, contaminant removal for a construction project. It was about a 6-week project where they were doing the same thing, construction dewatering. The water that they were having to discharge tested positive for PFAS, metals, and other organics. So Evoqua was contacted, and we mobilized a system that tapped directly into the wellhead, and it removed PFAS, arsenic, mercury, and other contaminants that were in the water. So it was a very robust system. I cleaned the effluent discharge and was put to a municipal sewer for further treatment. So it's not just one, it was a combination of other things. You can see by the picture at the top, there's different color vessels. They all look about the same size, as you can tell, but they also have different medias in there for removal. We currently have a temporary system operating in Colorado. It was installed to mitigate seasonal taste and odor issues, specifically MIB or methoisoborneol and jasmine. The municipality was planning on designing a new facility, but it wouldn't be available just because of the whole design and funding process and everything. But they needed a solution before the warmer weather season turned. So we did some bench scale testing because they didn't have time to run a pilot. We did some rapid small scale column tests. That's the RSSCT. We did some RSSCT testing to validate the system using granular activated carbon. We put some systems in parallel and installed it. It has been running about 3 months, and they're still running it below detection levels for MIB and the jasmine. The next case study is Kennebunkport and Wells Water District in Kennebunk, Maine. This is a very proactive water system. They detected PFAS as part of the UCMR3 testing back in 2016. They decided that before they implemented a solution, this was at one of their wells, one of the newly developed wells actually, they decided they shut the well down. They didn't want to run water through it, and they wanted to pilot several types of carbon to determine which perform best based on their local chemistry. And they are a very proactive water district in general, very hands-on, do a lot of things internally. After months of pilot testing, the results showed that a carbon made from our enhanced coconut product provided an additional 3 months of full-time runtime versus other carbons. And I'll get to some more information on that on the next slides. But they installed a full-scale high-pressure system to remove PFAS from the water. It's still operating, and they've been very happy with it. On the photo on the right now, if it's come up on your screens, is an actual photo of the pilot that was taken at the site. So you can see the influent, in this case for PFOA, was about 10. And that we had a standard coconut, which is kind of the black line, the darkest line. Then we had our standard 12 by 40 by 2 coal, which is the green line. Then we had our enhanced coconut product, which is our reactivated product, was a potable react product. That's the red line. And then we had our virgin enhanced coconut 1230CX, which is the yellow line. And you can see by the bed volumes that the CX product outperformed all the other ones and gave an additional 3 months of runtime to the overall operation. So after they installed the solution, they put a 12-foot diameter sand vessel up front to remove iron and manganese, injecting a little bit of chlorine. And then they had one lead lag GAC system, so 2 vessels in series. You can see that in the photo. They were both 12-foot diameter vessels. They put in about 34,700 pounds of the CX media into each vessel with a 10-minute empty bed contact time on the design, but 8 minutes on the actual when they're running at peak to handle the summer seasonal flow. It was originally an outdoor installation, as shown in this picture. They poured a pad and had it outside. But of course, being in Maine, the system had to be relocated into the indoors. They had put up a new building down the street and relocated the installation and the equipment over the winter when there was the lower demand on the water. So in this case, and you can see the bottom right picture, we use Evoqua as a SEPTA design, which allows for built-in flexibility. You can see those cones sticking up through the bottom, or the hats, kind of like they look like top hats if you see them, that stick up through the bottom of the vessel. It's a slotted screen that has a tremendous amount of surface area. It allows for changing of those slots or those screens without having to enter the vessel. If you look at the picture above, you can see there's a ring header at the bottom, so you don't have to enter the vessel to change out those. You can just drop that ring header after you've evacuated the media, and you can just change the septas, put it back in, and you're off and running. This allows flexibility in design because they're using GAC now, but they can switch to using resin in the future. The system went online with the Taurus, and it was a minimal impact to ratepayers. The superintendent said the goal was to continually produce drinking water with non-detect levels, and basically the impact to the ratepayers was roughly 3 to 4 cents a day, and they won't really see a significant increase for several years. And it kept them independent, which was what they really wanted to get out of this. And it was cheaper than buying water from an outside water utility or having to redevelop wells and do a whole bunch of other things. So it really met a bunch of their objectives by going with the granular activated carbon system in this case. Another case study here is in the southeast United States. It was a high TOC groundwater. This is another one where they went with a pilot system. You can see they started off with carbon. You can see the dark media in the column. It's a drinking water application. The source of the contamination is unconfirmed, but they had influent concentrations of PFAS, PFOA, and PFOS above the EPA LHA, Lifetime Health Advisory. The opportunity came in through an engineering firm that was working with the municipality on development and solution development, as well as trying to figure out how to put together a solution and do the hydro and geology part of it on how they were going to try and treat and determine the source. It was a challenging water. It had a relatively high amount of TOC for a drinking water, which is not uncommon in Florida. It had about 14 ppm of TOC, and their objective was to get it down to less than 10 ppt for their PFAS compounds. We piloted both GAC and IX. The picture that you see here shows the GAC, but they did end up going with ion exchange resin. So when we piloted the carbon, it basically, the high level of TOC caused fouling almost immediately. The pilot ran for several days before the pressure drop was so significant it wasn't worth continuing. So we switched out the carbon, put in ion exchange resin. Almost immediately within the first 24 hours, the resin turned black, but yet it still provided removal and continued to run without that pressure drop. So the piloting ran out to about 150,000 bed volumes, as you can see on the chart on the right. They were very satisfied with it, and they moved to a full-scale comparison of ion exchange resins with several providers and configurations. It wasn't just Evoqua. They provided other ion exchange resins, and they did a full scale. So they were running 4 vessels in parallel at a full scale and comparing performance. The full scale study, as I said, on the 4 different resins, showed here on the right, showed that basically Evoqua's PSR2 plus resin was one of the superior performers. They decided to spec in a SEPTA design to provide greater flexibility. In this case, they actually wanted to use a hybrid system where they were using a combination of carbon and resin in the same vessel. They used resin and then put a carbon cap on top of it because they had some concerns with taste and odor and color in the water as well. So using that carbon cap to help provide them with a little bit of aesthetic quality as well as removal of PFAS. So you can see that combination and going through that treated a greater volume of water and helped extend the media before it exhausted. So I know we're probably running real early here. We're probably about halfway into an hour. But Jeff, I'll turn it back over to you for wrap up.
Okay, thanks, John. So to wrap it up, our portfolio of comprehensive solutions. So we offer portfolio really from start to finish. Can rapidly deploy mobile assets to your facility, offer treatability studies to help identify the best available technology today. I think John did a great job outlining that in some of the case studies, and also offer permanent on-site solutions. We employ a dynamic servicing network able to be on-site in most of the U.S. within 2 hours, and our reactive generation services are there to help regenerate your media. And I'd say finally, our knowledge of disposal options, and this will kind of help you see the end of any waste that you have on site. So what could be the next steps? Where do we go? First, you want to assess risk on your site, determine the regulatory requirements, your surroundings, what's going on, maybe adjacent properties and things like that. Understand any public concerns, your brand recognition within your community. And then I'd say obtain some background water quality and perform some PFAS analysis. Really try to understand what you have come into your system and what else might be out there. So you can do several different analytical test methods for those. And then determine if there are any remedial alternatives. And by that, I mean, understand the lifestyle costs of the system. Maybe there's some destruction technologies that are now available. And take a look at your disposal methods and what options are out there for you. And then I would decide on what type of upfront site-specific testing methodologies you want to do. John explained pilot studies in detail, as well as the RSSCTs, and I think those are great options, at least to start your project. So with that wraps up our presentation today. Thank you very much, and definitely looks like we've got time for questions.
Yeah, thank you both. At this time, we will move into the question and answer portion of the program, and it's actually good that we've got quite a few questions that have come in. So we will try and get through as many as possible. And just a quick reminder, if you'd like to ask a question, you can still do so via the Ask a Question box in your presentation window, and we will get through as many as we can. Whichever we don't get to during this live event, we will be able to forward to the presenters to answer offline. So let's start off here with our first question. Looks like it's for John. John, what is the minimum time required to do an adequate pilot test for an 800 GPM groundwater system?
Thank you, Alana. For a rapid small scale column test or an RSSCT test, it'll take about 6 weeks, depending upon the incoming PFAS concentrations, in the water source, whether it's a surface water or a groundwater. For a pilot system with either GAC or resin, a pilot will take anywhere from probably about, like I said, 6 months, 9 months to a year, but you probably plan on about a year for a system of that size to make sure you got a representative, I'll say a representative run of the water.
Okay, and then, we got it. Let's see, for Jeff, do resin and carbon systems utilize the same type of pressure vessels? More specifically, can a GAC vessel be easily converted for use with resin?
Great question. A GAC vessel can be converted, so yes, to an ion exchange resin vessel. The inlet distributor, though, in outlet screens must be selected appropriately based on the size of the resin. So there is a slight change there.
Okay. Let's see. The next one is for John. What is the minimum time required to do an adequate pilot test? We answered this one already. Sorry. So the next one for John is, how do the costs compare between carbon and resin?
Thank you, Alana. Resin is typically 3 to 5 times as expensive as GAC, but when considering the empty bed contact time, the empty bed contact time for resin is 3 to 5 times less, or run times or run lengths between the media exchanges tend to be comparable. So you may have a much shorter empty bed contact time, so you're running at a 2 to 3 minute empty bed contact time for resin versus a 10-minute empty bed contact time for carbon. However, you have 5 times the volume, 3 to 5 times the volume, so the run times tend to be pretty comparable. But the PFAS composition of the influent, along with the overall treatment goals and bench or pilot scale testing, will determine the best CapEx and OpEx solution for which media would be best. Like I said, usually the initial CapEx for resin systems, like the vessels, since they're smaller, usually it could be a little bit lower. It depends on a lot of the other hydraulics, and if there's pretreatment necessary, usually involves bag filters and other things. But usually the OpEx is higher. With carbon, sometimes the CapEx can be higher, but the OpEx can be lower, when all things are taken into consideration. So.
Okay. And then the next one's for Jeff. What is the typical process for these projects from discovery to installation?
Okay, thanks, Alana. It starts with, after confirming detections, this would be for a PFAS project, confirm detections of PFAS by utility. It would start with the engagement of the utility's engineer, either in-house or external, for situational analysis and discovery. In many cases, speed is an important consideration when choosing a solution. So the solution used depends on each customer's specific needs. Because each site is different, we recommend pilot or bench scale performing tests, as we went over today. These tests, along with the customer's criteria, budget, timing, treatment goals, that will help determine the correct media in the system. So I hope that answers that.
All right, and let's see, for John, how does GAC perform for removing shorter chain PFAS?
Thank you, Alana. In general, GAC does not absorb short-chain PFAS compounds as well as IX resin. Both carbon and resin, however, have background water interferences, so you really need to, not to sound like a broken record, but you need to align your overall treatment goals with bench or pilot scale testing of the influent water to determine the best solution. GAC may not remove the short chains for as long a period of time, but if you have a system that ion exchange might not perform well on, you've got high chlorides, high sulfates, other anions that are going to compete, or you've got certain oxidants in the water that are going to be difficult to remove, then maybe carbon, while it may not carry the load, so to speak, as much as an ion exchange resin on some of the shorter chains, it might be the better or more economical solution in the long run. So. Thank you.
Okay, and then for Jeff, what about in situ treatment options for PFAS?
Thanks, Alana. Well, the carbon-fluorine bond in PFAS is one of the strongest in chemistry. The issue with in situ treatment methods such as oxidative processes is that it would require a large amount of energy to break down these bonds and ensure that the compounds were completely destroyed and that they're not forming other daughter products of PFAS.
Okay, we've got some questions still coming in. So let's see. I'm not sure who this question would be best posed to, but either of you can answer it. So does Evoqua provide monitoring of the effluent to determine when breakthrough is occurring?
You want me to get that?
Sure, go ahead, Jeff.
So, yeah, we could take samples and send them out to a laboratory to see what kind of breakthrough we're getting on that, or the customer can do that as well. We could advise on that.
All right. Let's see. Are there applications that have been developed and debugged for industrial wastewater, especially high TDS or TSS wastewaters?
I'll take that one, Jeff. So PFAS and wastewater has been an ongoing concern. There are applications for removal. The challenge, obviously, is it depends on what wastewater. If you're talking about municipal wastewater or you're talking about industrial wastewater, usually it requires more of a flow sheet overall design to treat at some of these places because you do have to remove suspended solids if you're running through some type of packed bed system to prevent fouling. In both cases of a carbon or an ion exchange resin system, you really want to avoid backwashing at all costs, particularly on the IX resin system. So upfront pretreatment is critical when you're dealing with a wastewater, whether it be municipal or industrial. Usually they can be very concentrated in certain things. So there's usually not only a dissolved solid or a suspended solid removal, but there's other things where you're having to make sure that you're pre-treating to remove other contaminants, whether it be BOD, COD components or other things in there to make sure that you're not going to, foul the resins too quickly or, whether the media too quickly, whether it be carbon or resin. There's not really a standard configuration on that, but it's really, I hate to say, it's more done on a case-by-case basis because every wastewater, as we say, the drinking water is different, but man, is the wastewater different. It's a far more comprehensive and far more complicated stream to treat.
Okay. So when incinerating resin, does resin supply heat energy, or does it require heat energy to be destroyed?
Jeff, I'll take that one. So resin, and since it's actually a thermoplastic, most of the resins are, some type of polystyrene or similar type bead. There's a BTU value associated with it. Now, we're not incinerators. Evoqua isn't in the incineration business. But from what we know in dealing with incinerators or working with them, so to speak, there is a certain component of fuel that has to be added. It's not a self-sustaining reaction, but there is a certain BTU value to the resin itself that adds to the overall incineration process. Thank you.
All right. Let's see here. So, do you normalize costs to compare enhanced coconut to IX resin? What about co-contaminant?
John, I'll let you
I'll take
that.
this one, Jeff. Yeah, that's fine. So when you say do normalize costs, so we I guess the answer to that question is yes. When we look at when we look at what technology we're using, whether it be if it's a coconut carbon or a, whatever media it is, a bituminous coal carbon or an ion exchange resin or whatever, when we're looking at it either on a bench scale or a pilot scale, we're looking at the actual, when we run these systems, they are done on a scaled down version of the full scale system. So everything is relatively scalable going back up, right? So that you'll be able to extrapolate between the two. Now, to a certain degree of accuracy, that's still an ongoing thing in the industry, is how accurate are these small scale versus full scale. There's just not enough information publicly available, so to speak, or available. People are still very tight-lipped about sharing of data because obviously it's a sensitive issue to talk about, what's in their water, and they obviously want to be very sensitive about really what gets released into the public's hands. So, and unfortunately, there hasn't been a lot of sharing among peers, so to speak, on what's been going on to be able to move this small scale, whether it be bench scale or pilot scale, up to full scale. But all the data is normalized to a standard so that you'll be able to, we take it and the calculations are done. We follow ASTM standards for our RSSCT. There's an ASTM that's done, so we follow that for scalability. So it's like I said, it's something that's traceable, and it's something that is, I'll say, normalized as part of the standardization of the testing. So thank you for the question.
So does Evoqua manage the spent IX or GAC after the treatment system is saturated? And if so, what is the process being used to do this?
So I'll take this one again. This is John. So Evoqua will help the end or the owner, right? Because technically the owner is the generator in the eyes of the EPA and I'll say the eyes of the law, so to speak. So they're the generator of the waste, whether it be whether it be carbon or resin, they actually own it. Evoqua will work with the generator on finding the best solution, whether it's carbon in reactivation, carbon in disposal through either, we don't like landfill, but either through reactivation or incineration. In resin, the same thing. There are some landfills that take PFAS. We don't usually recommend that. We do recommend incineration, but that's a decision that's made by the owner because it is technically their waste. They are the generator. But Evoqua will work with the owner on finding the best solution and finding the best deal and helping them manage that as part of the overall process. So Evoqua can't take ownership of the waste legally, but we will work with the owner or the generator to make sure that we get them aligned with the right option. So thanks for the question.
Okay, this next one's a couple of the technologies, such as granular activated carbon or ion exchange, state that materials can be incinerated after use. Doesn't EPA regulate the amount of fluorohydrocarbons that can be emitted into the air?
Jeff, you want to take this one?
Yeah, I'll take that. I'm sorry, I think I was on mute. Yeah, I think that's the jury's still out on that. There's some regulations looming about it, some talk about it. States like New York are looking at it as well. But that's really it. I think there's some standards that are still out there that could govern the emissions through incineration. I mean, there are ways to test it, so people have been doing that, but that's as far as I know.
All right. What would you suggest between a rapid test versus a full-scale pilot?
I'll take this one, Jeff. So it all depends. I mean, pilot, if you have the time and the budget, the other thing and the difference between the two is the pilots tend to be more expensive. They're longer, more labor intensive, more testing, so they cost more. However, you get when we do a bench scale test, we're taking a sample of water, typically a drum of water. So it's a snapshot in time, right? On the day you took that sample. Even if you made it up a composite over a certain period of time, it's still just a snapshot. A pilot, if you have the time, the budget, the resources to do it, is usually a far more robust way to determine, how the performance of your system is going to actually be in the end. You'll get a good idea of how long it will run, and to what limits, and you'll be able to see the performance over a longer period of time. With a rapid small-scale column test or an accelerated test, it's much quicker. Like I said, it takes months of time down to weeks. They're usually very accurate. They provide a much better view of a breakthrough curve than a pilot will, just because of the scalability of it. But so, I mean, it all depends on your particular situation. If you're in a rush and you don't have really the time or the money or the patience to go through a pilot, then a rapid small scale column is a very good test. If you have the time, the money, the patience to go for a pilot scale, it's a great thing to do. So we advise clients and engineers that it all depends on the situation. One of our things is every water is unique. That was one of the summary slides. Surface waters tend to obviously turn over more than groundwater sources. Groundwater sources are usually pretty consistent. Same with wastewaters and other things. Like surface waters, they can have they can either be very tight if it's something that's a very captive treatment process, or it can be robust. Where they may be, more, I'll say, in the plating world, we used to call it job shop, where you do one thing one day and one another. So for wastewater, it's the same thing. It depends on what your treatment goals are and what your influent is. So as I said, it can be, one or the other. Sometimes people do both, to be perfectly honest, just to kind of take a belt and suspenders approach. But it all depends on the time, the resources, and really the patience or the tolerance that you have for the amount of time it takes. So thank you.
All right, let's see. How are absorbents with PFAS managed for reuse and disposal? Emerging EPA standards governing discharge of industrial wastewater with PFAS. I guess that's just some background for that one.
I could take that one, John.
Sure.
So I'll answer the part 2 first. I guess the emerging EPA standards on industrial wastewater for PFAS is just something that's looming. It came out in draft for comment last month, and I forget the time period, but I think it's usually it's kind of by the end of the year the comment period is. So there's more to come on that. So we'll have to be watching that. I would expect to continue if whoever sent that question in to take a look at the EPA site and some other social media sites out there, even that will probably report on that as well. and my suspicion is that the national news will cover it too, because that'll be a big one. As far as absorbents, any waste on site, as John mentioned, our customers kind of own that, so we will work with you to come up with the best disposal options for that. Thanks.
All right, so we still do have quite a bit of questions, but all the unanswered questions will be forwarded to the presenters to answer offline. So if we did not get to the questions during this live event, we will get an answer later. And I just wanted to thank everyone on behalf of Waterworld and Endeavor Business Media. And I'd like to thank today's speakers, John Lombardo and Jeff Pelletier, as well as our sponsor, as well as our sponsor, Evoqua, for today's presentation, the value of single source providers of emerging contaminants removal, including per and polyfluoroalkyl substances. As a reminder, this presentation will be archived within 24 hours and can be accessed at waterworld.com for the next 6 months. A reminder email message will be sent to all registrants with a direct link to the archive. Please take a moment to share your feedback with us by completing the brief satisfaction survey at the end of the session. A certificate of attendance for today's webcast will be emailed to all registrants within 24 hours of today's event. And with that, we thank you for joining us today and look forward to serving you with future webcasts. This concludes today's presentation.